In this video, I want to talk about a couple of properties of functions. And the most important are these two here. As a function being one-to-one and a function being onto. Some other words for one-to-one and onto, sometimes one-to-one functions are called injective, sometimes onto functions are called surjective. And a function that satisfies both being one-to-one and onto, we call it bijective. So let's talk about what these mean. Starting with one-to-one functions, well, we say a function is one-to-one exactly when every element of your domain A is related to a unique element of B. So what that's saying is, if the output when you put in A equals the output when you put in B, it must be the case that you put in the same element A and B. If that's the case, then your function f is one-to-one. Let me draw a little example here. So a one-to-one function looks like this. So imagine we had 4 elements in our domain, and let's say we had, 6 elements in our codomain. Then this function in red that I'm drawing, this is a one-to-one function. Each element is related to a unique element in our codomain. So no arrow goes to the same element in the codomain. So this is one-to-one. This guy is not one-to-one. So let me draw something that isn't. So that would look something like this. 6 elements in our codomain, 4 elements in our domain, just like before. So something like this is not one-to-one, because this first element in our codomain has 2 objects from the domain mapped to it. So this is not one-to-one. This example here is one-to-one. So that's what one-to-one functions look like. Now let's talk about onto functions. These functions are where there's an element in your domain that's related to every element of B. And I'm being kind of loose here. That's not particularly precise. Let me be a little more precise. For all elements of our codomain, there is an element A such that if I plug in A into my function, I get B. Let me draw out an example here. So let's say we have this. Let's have our domain have 6 things, and let's have our codomain have 4 things. This function will indeed be an onto function, a surjective function. So let's have that mapped there, that mapped to the same thing. That's fine. You can have functions that are onto that aren't one-to-one. We know automatically right away this isn't a one-to-one function. That's okay. But let's continue this mapping. So maybe this function, the third element goes to the fourth element of our codomain. This guy goes to the second element. This guy also goes to the first element. Why not? And this guy goes to the third element. So this is onto. Every element of our codomain has something from our domain mapped to it. So this is indeed an onto function. For every element, you can find something you can input in your domain such that it outputs that element in our codomain. So that's how an onto function works. And let's look at something that's not onto. So again, let's have the same number of elements in our set. So something like this would not be onto. 1, 2, let's have those 3 go to this one, and let's have this guy go to this one as well. So you can see here, there's one element that nothing in the domain is mapped to it. So because of that, in fact, there's 2 here, the 2 middle ones. And because of that, it is not an onto function. So that's roughly the ideas of onto and one-to-one functions. And let's look at just a bijective function. It's just combining both ideas. I'm going to have the same number of elements in each set here, maybe 4. And there's a particular reason why I'm picking the same number of elements. In fact, maybe it's a good idea. Pause the video and see if you can intuitively think why I'm doing the same number of elements in the domain and codomain in order for the function to be one-to-one and onto. Okay, now that we're back, well, we could do something really simple. We could just have all of the elements just get mapped across like this. This is a bijective function. It's one-to-one. Each element is mapped uniquely from something in the domain, each element of the codomain, and it's onto. Every element of the codomain has something mapped to it. And we'll talk about why both of these sets have to be the same size a little bit later, but it turns out that that's going to be the case. Now, let's scroll down here and do an example. So we have this function. Actually, these shouldn't be the integers. This should be the real numbers. My mistake. This as well. So this is a real valued function defined by f of x is 3x minus 1. And I want to show that this is indeed a bijection. So we're going to look at some techniques to show this. So remember, if something's a bijection, that means it's one-to-one and it's onto. So we have to show 2 separate things here. So let's start with one-to-one. So to show something's one-to-one, basically the technique is exactly what you expect. Remember, one-to-one says if f at a equals f at b, then a equals b. So we're going to assume that f of a equals f of b, and we're going to show that a equals b. And we know something about f at x here. So let's go ahead and do this. All right. So we're going to assume that 3a minus 1 equals 3b minus 1. And we need to show that if that's the case, a does indeed equal b. Okay, so let's add 1 to both sides here. So we get 3a equals 3b, and let's divide both sides by 3. And you can see immediately that a does equal b. So this is what we're doing to show something is one-to-one. We're assuming that the outputs equal when you plug in a and b, and we're showing if that's the case, the inputs must equal. The other way you, of course, can think about it is the contrapositive. If the inputs are not equal, then the outputs are not equal. But usually this method is kind of the easier way of showing something is one-to-one. Now for onto, we want to show that there's a value in our codomain are, let's call that value b, such that if I plug in some a, I have to figure out what a it is, I get b. So let's choose an element in our codomain. So let's let b be an element of our codomain. Then we need to show that there is an A in our domain, even though these are the same set. It's just because the domain and codomain are the same set. So let's just be clear. This is my codomain here, and this are the real numbers, is my domain. So there is an element in our domain such that if I plug in a into our function, I get b. So no matter what element I choose in my codomain, I can find an a, so that if I input a into the function, it outputs b. Okay. So what does that mean? So we need an a such that 3a minus 1 equals b. And we can just solve for a now. And that a will do it, as long as it's in our domain. So we're going to solve for it, and then we're just going to check that it's indeed in our domain. So let's go ahead and do this. So we'll add 1 to both sides, and we get 3a equals b plus 1. And let's divide both sides by 3, and we get a equals b plus 1 over 3. So for any element of our codomain b, we can find an a such that 3a minus 1 equals b. And that a is b plus 1 over 3. And let's just check that this is indeed a real number. Well, it's always a real number. The top is, of course, a real number. The bottom, the denominator, is 3. It's never going to be 0. It's never going to be undefined. So this always exists. So this is indeed a real number. So we're good to go. So we can write a little sentence. I'm just going to write it up here because I'm almost out of room. We can say, since f is 1-to-1 and onto, it is a bijection. And we're done with this example. Fantastic. Note that the choice of domain here is important to whether a function is 1-to-1 or onto. If these were indeed the integers instead of the real numbers here, well, this function would still be 1-to-1 because this argument still works, but it wouldn't be onto. So pause the video and think about why that would be the case, why this function would not be onto if this function went from the integers to the integers. Okay, now that you're back, well, it's this whole expression here, b plus 1 over 3. This isn't always an integer. Imagine if b was the number 1. 1 plus 1 over 3 is 2 over 3. 2 over 3 isn't an integer. So if f was a function from the integers to the integers, it would still be a 1-to-1 function, but it would not be an onto function. So the choice of domain and codomain of your function is important. Let's look at another example here. We have a function g. The domain of g is a little different now. It's ordered pairs of integers, and the codomain are just integers. And the way we define this function is you input some ordered pair a, b, and it outputs 2a plus b. Now, we're asked to determine if g is 1-to-1 or onto. If it's 1-to-1, we should be able to do a proof like the above here to show it. And same with onto. We should be able to do a proof. But if they're not 1-to-1 or onto, then we should be able to come up with a counterexample for each of them. For showing something isn't 1-to-1, then there will be a situation where we have two non-unique inputs that give us the same output, two elements of our domain that map to the same element in the codomain, so elements in the codomain are not uniquely mapped. And if something isn't onto, then there's some element of the integers that just doesn't get mapped to from Z cross Z via G. So pause the video now and think about that, prove or find a counterexample. Okay, now that we're back, well, let's think about it. If we play around with it a little bit, can we come up with two pairs of integers we can put in here that give us the same output? And the ones that I came up with, well, we have something that's 2 times a number and something that's just that number. So maybe something like this will do it. So here's our counterexample to show it's not 1-to-1. And maybe you came up with a different counterexample, but if AB is the set, or is the ordered pair, 1, 0, then G of 1, 0 is 2 times 1 plus 0 is 2. And let's let AB equal, instead of 1, 0, how about 0, 2? Then G of 0, 2 is indeed 2 times 0 plus 2, which is 2. So we have two non-equal elements in our domain, 1, 0 and 0, 2. When we plug them into our function, we get the same output. We get 2. So this is not a 1-to-1 function. Okay, let's talk about onto now. Well, if we think about it, we need to come up with a way of mapping something here to every integer in our codomain via this rule. And if we think about it, a really easy way of doing it is just making a be 0. So this is indeed going to be onto, and we're going to prove it here. So pick an element in our codomain. Let's call it, we're using A and B already, so let's call it, I don't know, n. So we'll pick an integer. And we need to show there's some ordered pair that gets mapped to n. So that ordered pair is going to be as follows. Let A, B equal 0, n. So A equals 0, B equals n. Then G of this ordered pair, 0, n, equals, well, 2 times 0 plus n equals n. So if you pick any element you like in your codomain, you can find an element in the domain, this one is 0, n, that gets mapped to that element n. And remember the order of quantifiers here. You have to pick your value in your codomain first, And the existence value, the one you need to find, can depend, and in fact, and a lot of times, should depend on the thing you picked beforehand. So in this case, it depends on n. It's the ordered pair 0, n. So this function here, g, is not 1-to-1, but it is onto. Let's look at one more thing here. So this really talks about the sizes of sets for bijective functions. It's a very, very strict what you can have. So what we're going to show, if we have a function from a to b, where a and b are finite sets, and we know, in this case, a is smaller. If a is smaller, if your domain is smaller than your codomain, the function is never onto. And in kind of the opposite direction, if the codomain is smaller than the domain, then f is never 1-to-1. So the result we want to deduce is that, well, for a function to be bijective, what can we say about the sizes of a and b using these two things? So I'd say pause the video now and see if you can prove this. Okay, let's go ahead here. Let's call this first one, let's call this 1. And let's call this guy here 2. So let's do 1 first. And hopefully, when you were thinking about this, you might have thought, well, we have something expressed as not something, so it might be easier to do the contrapositive here. So that's what we're going to do. We're going to assume that f is an onto function, and we're going to show that it must be that a has to be greater than or equal to b. Okay. So let's go ahead. Assume that f is onto. Well, if f is onto, and let's let the size of a be n, I guess. So remember, if a function is onto, then every element in the codomain has something in a mapped to it. So if there's n things in a, at most they can be mapped to n different things in b. So at most, a can be mapped to, or let's say elements in a, that's probably more clear. Elements in a can be mapped to n different elements in B. And you can think about that via a diagram, right? So let's say if there were 3 things in A, they could be mapped to, at most, 3 things in B, if they never double up. We know F is onto, which means that there's no elements that aren't mapped to by something in A. So, this means that B, the size of B, can be, at most, n. So the size of B is less than or equal to the size of A. So, by contrapositive, we assumed F was onto, and we showed that A is greater than or equal to B, but we wrote it this way: B is less than or equal to A. They mean the same thing. So, we've proved this by, and let me be clear here, this is by contraposition. Let's do the second one now. If you didn't manage to prove this before you watch the video, maybe it's a good idea to pause the video now, and now that you have kind of an argument to look at and modify, see if you can do a very similar thing for the second part with the one-to-one bit. Okay, now that you're back, let's do contraposition again. So let's assume that f is 1-to-1 this time. And again, let's let the size of A be n. Well, this function is 1-to-1. So what does that mean? So that means there are n different elements mapped from A to B by our function f. Now, there could be some elements in B that don't get mapped to by f. That's fine. The function doesn't have to be onto it. We just say it's 1-to-1. You can kind of see that in this diagram here. So we know if we have a function here, because it's 1-to-1, each element is mapped to a unique element in B. So B has to be at least the size of A. This means that the size of B is at least the size of A, which we called n. So we have that the size of B is greater than or equal to the size of A. And again, by contraposition, we assumed the negation of the then part. So f is a 1-to-1 function, and we showed that the negation of the if part is true. So that means that B is greater than or equal to A, which is what we've shown. And our conclusion, well, remember, 1-to-1 functions have to have the codomain less than or equal to A. A 1-to-1 function has to have the codomain greater than or equal to A. So if a function is both 1-to-1 and onto, the only way that's possible is if the codomain equals A in size. So, since a bijective function is both 1-to-1 and onto, it must be that the codomain is greater than or equal to the domain in size, and the size of the codomain must be less than or equal to the size of the domain. So the only way that that's possible is if the sizes of both sets, the cardinalities, actually equal each other. So that's a nice key result. Bijective functions have the domain and the codomain having the same cardinality for finite sets. That's important. Okay, so that's all I want to talk about for properties of functions. We're going to move on in the next video to talk about inverses, how to turn the arrows backwards in functions, where the codomain is now your domain and the domain is now your codomain.